In this example, I'm going to show you using the k-nearest neighbor algorithm to do some modeling on an example data set. In this data set, we are trying to predict whether someone will make a term deposit in a bank. That is, they put their money in for a defined period of time. And this data has some information about demographics for these customers, and it also has some information on the marketing campaign. And this is our outcome variable, whether or not they actually did a term deposit or not. Before we begin modeling, it's good to look to see whether some of the numeric variables have a strong or weak correlation with the outcome variable. So what I did is I took this column and converted this into a number of 0 for no and 1 for yes, so that I could evaluate how strong these numeric variables were with this outcome variable, because it provides sort of a useful first glimpse into what's going on. This is the result that came from that process. Here is our outcome variable, and as I look down at these other numeric input variables, really none of them have a very strong correlation. The strongest correlation we see is about 0.11. So this is good evidence that this is a tough sort of modeling problem. If you have something much stronger here like 0.4 and 5 and 6, something like that, you know it's good evidence that you're going to have an easier time getting your predictions to do really, really well. But sometimes the data looks like this. There just isn't any really strong correlations with your outcome variables. Now, I can also look at the scatter plot matrix, and this is also showing that these relationships are not really very perfect in terms of straight angles, in terms of positive and negative relationships. Before we do this, let's go ahead and set up our data partition. And so what I want to do with this situation is, when you're doing your k-nearest neighbor, it uses the validation column to figure out how many nearest neighbors gives you the best results. And this allows for the possibility that while you're doing your validation, you're introducing some overfitting. And so we're going to just check for that. And so what I'm going to do is I'm going to put a 0.5, 0.3, and the remaining 0.2 for a test set. What this will let us do is we can use the validation data and let it learn what the best n is for the number of neighbors, and then we'll take that algorithm that was defined in that way and we'll put it on the data that it has never seen before, and we'll see if it has overfitting. In other words, if the test data set has a higher degree of error than the validation data set does, it's a pretty good indication that there's some overfitting in the validation set. So I'm going to call this just three-way. For a three-way validation, I could have called that anything, and I will go ahead and set a random seed and generate our validation data. So here is our validation column, and we're ready to go. So now I'm going to analyze this with our k-nearest neighbor. There is our validation, and there is our outcome variable, and we're going to take all the remaining input variables and put them in here. A good number to start with is 15 nearest neighbors, and so the algorithm will look at 15 and then 14 on down to 1, and it will let us see which number of nearest neighbors actually produces the best result. So I'm going to do this now. It takes a few seconds for the algorithm to run because it's very data processing intensive, and here are our results. What we see in these results is there are 3 classification matrices down here, and we can also see which number of neighbors, as shown here in the K column, actually produce the best estimates. That is the lowest misclassification error rates. So if we go over here and look at the validation data, we can see that the number 10, when K equals number 10, then the misclassification rate is about 11%. If we go over and look in the test data set, we can see that the misclassification rate actually went down instead of going up. This is good evidence that we're not introducing overfitting when we use the validation set to figure out what the best number of nearest neighbors is. And so I'm feeling pretty confident now that I can not have this step. Now, if you go look at some of the data mining competitions like on Kaggle, very often they'll have 3 data sets. They'll have a training set, they'll have a validation set, and then they'll have a test set. And the idea there is that they're controlling for the possibility that you might be introducing overfitting in your validation process, and so they have this holdout set that is a test set that is independent and is not really touched at all by the training or validation process. So it's good to know there are a few algorithms like KNN that might introduce overfitting in the validation set. So this is why we kind of go through this process of checking to see if we're introducing overfitting or not. Since we're not, I'm going to get rid of this column and I'm just going to do a training validation split. We've sort of controlled for that problem, so we'll just generate a new validation column and we'll do something more traditional. We'll just do 0.6 and 0.4. Leave it as validation, set a random seed, and generate our validation set. All right, so now we've done this. Now we can go ahead and do our nearest neighbors and use this validation instead. Here are the results. Here we're getting error of about 10.5%, and in the training data we were getting 11%. So we're actually doing better on the validation than we were on the training. So we're really not having a lot of overfitting going on. In fact, there's no evidence of overfitting going on between the training set and the validation set, and that's a good thing.